So now the question is, where do these UV coordinates come from? So for something simple like a cube, we can just figure out how to put them on there. As the objects get harder, we're going to have to figure out something else to do. So in general, I have my 3D object, and I have some 2D texture, and I have some function that maps from my 3D object to my 2D texture. So any way I can define a function is going to work. So we can define a simple function. Well, let's just put a cylinder around this thing, project the points, right? X, Y, Z goes to r theta height. We could just throw away r and use the theta and the height and then map onto this texture. So we could do something like this. This will cause trouble. So it's easiest, where's it easiest to see the problems that this is going to cause? Maybe on this teapot handle. So the projection, this part is yellow and this part is yellow because they're both on the same cylindrical projection. So it'd be impossible to have a different color here from here if we use this. But this would be one way to get the job done, and it works for some simple objects. If we made these things out of Bezier patches, then we have some natural parameterization, right? So if we're using some sort of spline patch, it has parameters, S and T, in order to define the splat. The patch, we could just use those to map our texture. That would work. A place where you've all seen this is mapping maps, from the world onto maps, right? So like, here's our texture, here's our spherical object, map your texture on here, you're supposed to get what the true world is. This is a nice example to show that it's not unique, right? We often see maps that are like this, but I can draw a map in this kind of form, right? This is some other projection. I'm sure you've looked at these before. There's hundreds of different projections for maps to preserve different properties. I could use this for my texture map and still get it back onto my sphere in the right way. It's harder when your objects get harder. So now suppose I want to get this nice checkerboard pattern onto my cow. What are the UV of a cow? Well, not really well defined. People write research papers about this kind of thing, right? I need some function that maps all these points onto UV. There's not an easy way. In the basic idea is that you try to find a cut place on your object, right? So this cow is topologically the same as a sphere because there's no loops. It's not a torus or anything like that. So for this, you try to find a slice point where they've now put it on the bottom of the cow, and you try to open it up and flatten it out, and then you can map this onto your texture object. So this is the general kind of idea of what do people do, but it can be arbitrarily hard. So here's an example from an artist tool. This is Maya. And here's their UV editor, right? It's one of the tools they give the artist. So I have a 3D object. I want to map where the UV goes onto this thing. So here's my texture map, and I'm trying to control this mapping. These are the kinds of things. So the process of getting texture coordinates is not simple, right? It would not be an acceptable intro graphics class for me to give you a cow or a character and say, oh, automatically derive UV. Typically, when you load a model, if I just go to the net and pull a model, the model either will or won't have UV coordinates. And if you wanted to apply the texture, you would wish it had UV coordinates already applied to the model and stored in the file. It's not something you would want to calculate. But for simple things like spheres and cylinders and cubes, which we're building our things out of in this class, then I can ask you, just go write the code to apply the UV. And indeed, that's what you're going to do. Okay. Questions up to this point of finding, we talked about finding UV and where do they come from? Is there any questions people want to ask surrounding this? Okay. So now we come to the hard part of texture mapping. So I think the part we talked about is pretty simple theoretically in terms of what's going on, but there's some gotchas that keep it from really working the way that you wish that it would work. So if we look at where things land in the texture space, we're going to see that it's non-uniform. So consider here's a triangle. We've specified UV at the coordinates of this triangle. It's been rasterized, meaning figure out which pixels are turning on. This is something the graphics card is doing for us. And then we get to a pixel, we're running our fragment shader, and we're going to go look up in the texture, right? We have an interpolated UV value. We go look it up, and it lands here in our texture. And then this one lands here. The third one goes here, and the fifth one goes here. Now, something we should notice is that in screen space, these had uniform spacing. But in texture space, it's not guaranteed to be true. It could be that some of these samples are packed close together, and some of these samples are packed far apart. And in particular, when they get really close together, do they get the same color, or how should the color vary? And when they get really far apart, did I miss some details in between that I skipped over, right? And there's supposed to be something in here and I didn't see it because it falls between these. Can this happen? Yes, for sure this can happen. So we're going to look at these two cases separately. Let me try to give some more illustration of what the problem is first. So here's a source image. And here we've rendered it at 256 by 256. So there was a texture applied to a field. In the back, we can have aliasing artifacts that happen when we don't have enough pixels to make up for the texture. And in the front, we can have these jaggy artifacts, which are happening from the other side when our pixels map too closely together into the texture. So we can have both of these moire artifacts in the back and these jaggies in the front. So we're going to end up looking at those. So where does this come from? So here's our screen space. So our pixels are evenly spaced. Here's our texture image. The texture image is not going to change. I'm going to show a sequence of examples. So here we've shrunk down the texture image and placed it smaller on the screen. So what does that mean? That means our screen pixels, right? These are both 600 pixels wide, but we've now shrunk it down. That means the screen pixels are going to have this wider spacing and texture space. Right? The white ones are the texture space. The red ones are where the screen pixels landed. So they've skipped over stuff in between. So this is minification. We can go the other way. If we blow up the texture and zoom in, then our screen pixels, there's too many of them. We don't have enough texture to cover all of them. So we're going to end up having to reuse colors on multiple screen pixels. This is called magnification. In general, the problem is this. For a screen pixel, the area that it covers in the texture might be tiny or might be huge, and it's going to depend where you are in the picture. There's no single answer. So I can't set my texture size because back here, I covered a lot of pixels. And then up here, well, my screen is even smaller. I wish I had more pixels in my texture. So to be clear on our naming, magnification is when we blow up the picture on the screen, and that means our screen pixels come out as tiny things in our texture space. When we do minification, this is when our camera is far away, and so the texture looks small on the screen. One screen pixel maps to multiple texture pixels. So the screen pixel is really big in the texture space, meaning there's too much information in the texture. Over here, there was not enough information in the texture because the next pixel, we really didn't have a separate piece of information. So these are the two problems that can occur.